Good morning, everybody. I'm Sunjun Kim from Keist, and we supervised by Geehyuk Lee from SIGCHI lab Keist. I'm now introducing you TapBoard 2, which is a combined pointing and typing interaction on a multi-touch surface keyboard. The motivation of this work is the burdensome of the switching between keyboard and mouse or between keyboard and touchpad. And of course, there are many solutions, so many attempts has been done to combine typing and pointing in same space. These works embedded pointing functionalities on physical keyboard and virtual keyboard in various ways. During this work, our previous work named TapBoard at Keystrokes 2013, which is accept only tapping as a keystroke and ignore others for other purposes. The other purposes, meaning at Keystrokes 2013 was some kind of text character manipulation. In this case, TapBoard 2, which is used non-tapping gestures for mouse cursor manipulations. More precisely, non-tapping gesture in this case, meaning a dwelling or dragging gestures. We'll visit them each interaction one by one. Of course, keystrokes are done by taps, and dwelling and dragging are used for manipulating mouse cursors. This is a basic concept, and we implemented two different types of the mouse clicking gesture. One is named add finger gesture, which is done by adding one tap while manipulating the cursor. And another one is named the tap gestures, which is consecutive tap after releasing a manipulating finger. So those two gestures are mimicking a touchpad interaction. The former one is that clicking a physical button, and latter one is the traditional tap to click gestures. And to support some additional interaction to support more regular mouse operations, such as drag and drop, in other words, button press and hold, additional finger dwell during cursor manipulation, acting button press and hold, and two finger scrolling, working as a mouse wheel scroll or scroll gestures. This gesture set mimics the regular touchpad operations, so we expect users to adapt this concept very easily and quickly. And moreover, these gestures are designed to be coexist with typing operation without any conflict, so without any mode switching. And we first attempt to implement this idea with a finite state machine. However, as gesture increases, more states are recurred, and the transition between states are increased in exponential manner. So that we need to define some more systematic approach to implement the algorithm to detect the gestures. So we found that most of transitions in our finite state machine happens when the finger count changes and when dwell time lapse or finger moves some more than some moving distance. Interestingly, most of previous works on gesture on touchscreen keyboard also relies on similar actions. Therefore, our algorithm can be generically applicable for those applications also. Given that those three features, we developed a simple and effective gesture recognition system as follows. We'll visit them one by one. The first item is that defining touch paces for each touch point. And this definition takes moving distance and dwelling time into account. In TapBoard 2 system, a touch point may have one of the three paces, which is a touch, dwelling, and moving. Every touch point starts with a touched pace, and after a certain amount of time, it goes to dwelling pace, in this case of 450 milliseconds from our previous work. And from those two states, after the cursor moves more than a certain distance, in this case 5 millimeters, it goes to moving pace, and moving pace is the final phase until the lift off. Okay, now we define the touch paces and move on the system state. A system, in other words, a multi-touch device, may have a multiple touch point having different touch paces. And the system enumerates the number of touch points in these different paces and represented as three numbers. And these three numbers indicate the so-called system state. Now we move on to define a gesture. which is defined as a sequence of the system state. For example, when user interact with the system changes state over time. For example, user land the finger and then lift up. Then these three numbers are changing history of the system state and define the tap gesture. For another example, user land on and slide and lift up. And this is defined as a drag gesture, those four numbers. So with this system, we could implement proposed interaction with set of numbers as like in right side with very ease of implementation. And we evaluated those design interaction and gesture recognition system with following setup. The system consists of one Microsoft Surface tablet, and the tablet generates a legacy USB keyboard and mouse signal to the experiment evaluation system. We prepared three conditions. The first one is the CA, which means the combined and add finger gesture interaction, and CT for combined and tap gesture interaction. And as a baseline, ST means the separated tap, which uses two devices, one for the keyboard and one for a touchpad. Let's look at each condition in more detail. Combined add finger condition use left hand to click, and combined tap condition uses a release and tap strategy for click gesture. And separated ST condition uses two separate devices and user need to switch between two devices. We prepared 18 participants, which is gender equalized, and we designed the within subject design. And each participant tried 243 trials for each participant. Each participant tested three conditions, all of the three conditions. And the task including pointing and typing was designed. The pointing task was the feature style pointing task, and after that, you just need to type a short word consists of 5 to 7 characters from random corpus. So basically, this is a pointing and typing repeatedly. We'll briefly report the key findings. So for more details, please check our paper. CA condition, combined add finger condition, thanks to the bimanual interaction, it's having a more better feature throughput. And combined condition discriminated pointing and typing with more than 96% accuracy. However, some discrimination error slow down the combined conditions typing speed about 2 WPM. And more interestingly, most participants, means 15 out of 18 participants like the CA the most, and CT for 2 participants, and only 1 participant like the ST, the baseline condition the most. We can applicate, for application, we may apply this approach to dual screen laptop and dual screen desktop like HP Sprout, which is displayed in basement, and for regular touchscreen keyboard to simulate the mouse operation with a multi-touch surface. And we can expand this work to the physical keyboard to combining the typing and pointing integration. Okay, to conclude, I introduced the touchpad-like TapBoard to interaction and evaluated that with higher accuracy and high user preference. So I'm happy to take your questions. Thank you.
Yeah, so these the crosstalk between I'm typing or I'm pointing is always a confusion. Of course, back with JPoint, there was, and I did some in-keyboard pointing device work also. But you say that there's a 450 millisecond dwell that you require to start, and that's an awful long time. Is it what do you think about that dwell, the half a second dwell that you need to start recognizing?
That threshold actually came from our previous research, TapBoard, at CHI 2013, and participants are asked to rest and typing for, I mean, in other words, dwell and typing, and we found that threshold from those data. Yep.
Hi, Daniel Ashbrook, Rochester Institute of Technology. You mentioned implementing it on a physical keyboard, and I'm curious how you would be able to do that.
Actually, we need word state, for example, touch and press state for application and physical state, so we need to re-implement the system, redesign the system to application on a physical device. So that might be our future work.
What about the actual sensing of the touch?
Excuse me?
The sensing, how would you sense the touch on the keyboard?
There are a number of implementations, such as the touch display keyboard that senses the keyboard. And in our previous work, we developed the keyboard having electrode to sense the touch. Or we can implement the capacitive sensor array beneath the keyboard to detect whatever, moving and touching. Yep.
Cool, thank you.
Thank you.
All right, this concludes the session. Let's thank all the speakers again.